Okay, so thank you everyone for coming. My name is Yash, and I am a third-year data science and cognitive science major. And yeah, it's glad to have you here. And yeah.
And I'm Ishaan. I'm a second year, third year CS Bioinformatics major, and it's my first time doing this workshop. It'll be great. Glad to have you all.
Awesome. Yeah, and we're going to go through an introduction to machine learning using SKLearn. And yeah, we're glad to have all of you here. So before we begin, there's this repository, and yeah, if Ishaan, you want to just copy and paste the link into the chat.
Sure.
Yeah, our attendees can you can follow it along with this. And this will have all of the demos that we're going to be going through in this workshop. And Ishaan will be leading our demo section later on. And yeah, so you should be able to either follow on by clicking the Python notebook within that repository, or you can clone it to your local device and just open the Python notebook in whatever, you could open it up in Google Colab, you can open it up in Jupyter Notebook or Jupyter Lab, whatever you're most comfortable with. And then make sure to download the CSV as well, since that has the data that we'll be using. All right. Cool. And then today what we're going to be doing is going over just an overview of what machine learning is and the categories of machine learning, which is supervised learning and unsupervised learning. And then we're going to be going through some of the main tasks that you will face in machine learning, which are clustering, classification, and regression. And then we're going to have a demo led by Ishaan on the Pokemon dataset that is in that repository. And we'll be going through some of the commonly used algorithms within these main tasks. So yeah, this will be a pretty cool workshop, and we're really excited for it. Okay, so to start us off, so what exactly is machine learning? And I'm sure this is a buzzword that you all have definitely heard a lot, especially in recent years and maybe even in your classes. But pretty much what machine learning means is it's using patterns to teach computers how to learn and act without explicitly being programmed. And here you want to feed it data, and this would create predictions on unseen data. And this way you want computers to learn from the data and be able to make valid predictions in the future. And yeah, so machine learning models are generally dynamic that can learn from themselves, predict, and improve. And machine learning is very dynamic and fluid, so it can use multiple types of data, which is why it's so applicable nowadays, because many companies will be dealing with different types of data, such as numerical data, text, images, or time series. And there are countless applications of machine learning. So like image data could be used if we want to predict what something is. So if we're programming a self-driving car, we could use image data to help it drive around, and use a scanner like a LiDAR scanner to determine what an object is and determine if that's an obstacle and how to drive around. So there are a lot of applications of machine learning, and yeah, it's a very broad field. So now we're going to talk a little bit about the categories of machine learning. So the first category is supervised learning. So when you think of supervised learning, what you should think about is labeled outputs, and that is the key here. So what you're doing is you're using a data set that has labeled outputs to determine a predictive model. And here, what you'll be doing is the data set that you will already have those desired outputs. And that is the way that you can determine how accurate or precise your model is. And within supervised learning, we do have some categories, and these are classification and regression. So classification is, as the name suggests, you'll be classifying points of interest into different classes. So there is binary classification and multi-class classification, and we're going to be going more in depth into these later. But yeah, when you have binary classification, you're categorizing data into one of two classes. And if you have multiple classification, it's like multi-classification. It's when there are three or more classes. And then regression is finding a relationship between one or more independent variables and then a dependent variable. And this is often used in forecasting or prediction. And yeah, you can look at this, this graphic right here. So when you're inputting data, you're going to have the algorithm that uses the training data set with the desired output. And then you're going to process it and you'll have the output. So here you have 3 different classes. So this could be a multi-class classification example. So now the other category we have is unsupervised learning. And this one is it's a little bit more complex because you have an unlabeled data set. So you're not going to actually know what the result is. So in supervised learning, if you have a data set that has house prices and the features of the house, like the number of bedrooms, the number of bathrooms, the location, and then the label is the price, you could think of an unsupervised data set would be one that doesn't have that label of the price on it. So yeah, unsupervised learning has different categories, different tasks, and these are clustering, anomaly detection, and dimensionality reduction. So clustering is when you want to discover groups within data. And yeah, so this is when you have several data points and you want to categorize them based on similarity. And then anomaly detection is very commonly used in business practices. It's used many times with credit card fraud. And this will be singling out any outliers or unusual points that don't seem to belong. And then there is another application that is a little complex. It's called dimensionality reduction. And what this means is if your data set has multiple features, each feature adds another dimension to the data or to the algorithm. So what you want to do to simplify your algorithm is to use dimensionality reduction to determine which features are actually relevant and which are the best predictors of whatever you're trying to accomplish. So those are the most important features. So you want to reduce your data to only include those features. Yeah, and here, as we see in the graphic, the difference here is that there is no training data set. So what that means is since we don't know the output, it's unlabeled, we will not have that training data set. Whereas in supervised learning, since the training data set will have the label there, the test data set, we will exclude that label. We would have, since we know the output there. But here, since there is no output known or known label, we would just input all the data, process it using the algorithm, and then have our desired data processing. Okay, and now we're going to go into the major types of machine learning techniques or categories. So yeah, so the first one that we're going to talk about is classification, and we already went into a little bit of this. So it's categorizing data into binary or multiple classes. And yeah, binary classification would be identifying or classifying data into one of 2 classes. So yeah, one common example that you'll see in your class is identifying spam emails or not spam emails. So this is a pretty common application, and yeah, this is one that you'll see in class once you take, I believe it's DSC 40A. Yeah, so you could, based on the features of the email and the contents of the email, you could identify it as an email that's spam or one that's not spam. And this is sort of what happens in your inbox when you receive mail. There would be some algorithm behind the scenes that, or under the hood, that determines whether whether that email you just received was spam or not spam. And then there's multi-class classification. So one example of this is recognizing handwritten characters. And the reason why this is multi-class is because in the English language, there are 26 letters. And if we want to classify a handwritten script into a letter, we would have several different classes that we could classify it into. So that's why it would be a multi-class classification problem. And then yeah, classification uses supervised machine learning techniques. So what that means is that the data is labeled. So when you're training the data, if you're doing the spam data set, you would know that the email is a spam email. You would train it using that knowledge. And then some common algorithms we'll see within this is naive Bayes, k-nearest neighbors, logistic regression, and decision trees. And we're going to be covering the first three in this workshop. So naive Bayes, k-nearest neighbors, and logistic regression during our demo. And then we also have regression. So regression is finding that relationship between one or more independent variables and then a dependent variable using least squares regression. So what least squares means is so this has a mathematical foundation, and what it wants to do is find the least squared error between your points, between your estimation and true points, and it would fit a model to that data. And so there are two broad categories within regression, and these categories are simple regression and multiple regression. And simple regression is when you would have a prediction based on only one explanatory variable. So if we wanted to predict the rent of apartments in San Diego, we could predict the rent based on one feature. This feature could be income. It could also be like the rent based on the number of bedrooms in that apartment, and just solely that feature. And yeah, so this if it seems pretty if it doesn't seem very practical that you'd be using one feature to predict like rent, you're absolutely correct. Simple regression is not the more commonly used one in real life. It's not more realistic because as you know, there are multiple factors that go into predictions. So for rent, there would be multiple factors, such as it could be your income, the number of bedrooms. It could even have something related to the location, like the humidity of the location. It could also have like the school, like something about the schools nearby. So these would all be different features, and it's called multiple because those are variables that are those are all different independent variables. And then within, as if this wasn't complex enough, there are more categories within simple and multiple regression. And this is called linear and non-linear, simple and multiple regression. So the linear and non-linear talks about the actual model. So what you're going to be fitting the data into, like that predictive, like whatever line or polynomial, so whatever is linear or non-linear that you're going to fit to the data. And so this could, if you're talking about linear regression, you'll be fitting a line to the data. And if you're talking about non-linear regression, you're going to be fitting something else, like a polynomial function or a logarithmic function or a square root function, something like that, to the data as well. And then the simple versus multiple. So if it's simple, it'll be in 2 dimensions. If it's multiple, it'll be in higher dimensions. So linear and non-linear, just keep it, try to keep that like aside from simple and multiple. And then when you're talking about simple linear, try to connect the two. So simple will mean 2 dimensions, which means one explanatory variable, and then linear means it'll be a line. So you could have any combination. You could have simple non-linear or simple linear, and multiple linear, multiple non-linear. And then here again, you're going to be using supervised machine learning because you will have the label of whatever you're trying to predict. Like you would have the labeled rents for the houses that you would want to predict the rent for. And then Ishaan said you don't want to miss important features, but also not give too many features. Ishaan brought up a great point. That's called overfitting. So when you overfit data, that would what that means is your line or model that you create, it just depends. It really depends too much on whatever data you've given. So it'll break when you bring in other data because you fit it too much to the data that you've trained it on. And that's something you want to balance when you're making a model. And that was a great point, Ishaan. And then some common algorithms, as I said, were the simple, multiple, non-linear regression. And there's also lasso regression and support vector machines. And those are a little bit more complex, but we're going to be going through multiple linear regression in this demo later on, since that is a pretty common one. And then you have clustering. So clustering would be discovering groups within data. So the most common one is centroid based, and this organizes data non-hierarchically. So what that means is it'll just categorize your data into different groups without putting any order to it. So it won't say that like this group has a higher, like this group is like a parent group to that one. It won't say that. So it'll just separate your data into groups. And this is usually based on like distance. And yeah, this would be sensitive to outliers because any outliers would sort of change the distances, and that could affect how the groups are made. And then density based, what that does is that's another type of clustering, and it connects areas based on their density, and it would ignore outliers. And then this is different from centroid based because in centroid based, the clustering was based on some randomly initialized points. And then it calculates the minimum distance from a point to the other points. And then distribution based is a little bit more complex. This one is when you're clustering data into various distributions and you put them into groups depending on the probability that that point would reside within a distribution. And then there's also hierarchical clustering, and what this does is it creates trees of clusters. So it would have like one cluster is a parent group of another cluster. But you're most commonly going to be seeing the centroid based one, but just wanted to make you aware that there are other types of clustering. And then clustering is an unsupervised machine learning technique, which means that it is unlabeled. Your data is unlabeled, but your algorithm will learn as it goes along. And there are many common algorithms, but the one that we're going to go through today is k-means clustering. All right, so now we're going to go through that demo. And if you haven't gotten that Python notebook open, yeah, I think Ishaan, do you want to send that link again in the chat?
Sure.
So all of our attendees can open up that link, and you can open it in Colab or Jupyter Notebook, whatever you're more comfortable with. Ishaan, Ishaan will be presenting it live, and yeah. So if you're looking at this screen and are like, wait, we're talking about Pokemon, but these do not look like Pokemon. Like these look pretty horrific. Yeah, you're absolutely correct. Like these Pokemon were made. These are fake Pokemon made on. They're constructed from features of different Pokemon. So you might see some similarities to them, but to ones that you know, but these ones were created by an artificial algorithm. So it's really weird, but yeah, it was pretty interesting. Okay, so yeah, so the first algorithm that we're going to go into is naive Bayes. And yeah, so naive Bayes is commonly used for both binary classification and multi-class classification. And this is fundamentally just based on Bayes' rule, which is a formula in probability that, yeah, it's one that you'll learn in DSC 40A, but also you might learn it in math classes like 183 or 180A. And Bayes' rule, what it says is it sort of predicts the conditional probability that so it predicts the probability that that your data point will reside in the class given that data feature. So yeah, on the left you'll see like a skeleton you'll see the skeleton rule of Bayes' rule, but then on the right side you can see a more applicable version of it. Like it's how we use it for machine learning. And yeah, so we would say that the probability of the data point belonging in that class, given the data's features, is equal to the probability of the data being given that class times the probability of that class divided by the probability of having that data. So this is called naive because it has the assumption of conditional independence between the predictor variables. And this is really unlikely because it's really unlikely that your predictor variables are unrelated. So yeah, like if you're talking about the rent prices of a house, it's pretty unlikely that so if you talk about San Francisco versus a rural area, so if you talk about San Francisco versus a rural area, San Francisco apartments will probably have a fewer number of bedrooms, and these two predictors are definitely related. They have some sort of relation. So if you would say that these were completely independent, like if they had conditional independence, this is a pretty naive assumption. So it probably wouldn't create a good classifier. Yeah, and then the way that we would do this is for each class, we would calculate this probability that it belongs in that class given the data. And at the end, we would select the class where the probability was the highest given those specific features. And yeah, so now Ishan's going to give a demo of using naive Bayes to classify Pokemon types. And yeah, let me just stop my share and then Ishaan can take over.
All right, so I'm going to share my screen. Let's go. So we just saw naive Bayes, and first of all, we're going to prepare the data for applying all the tool machine learning stuff that we're going to do it. So the data set that you have is present in the CSV, right? So we're going to be reading that CSV file using pandas, and this is what the data frame looks like. So we have name, attack, defense, height, percentage male, SP defense, right? You see a mix of categorical data, like, well, name is one of them, type is one of them, and then you see many numerical types. Another thing you can see here is that we have lots of missing values here, NaNs, right? So the first thing we want to do is, okay, let's first see how many missing values do we have. And what I'm doing here is just going to be seeing the shape. What if I drop my missing values? What will the shape change to? And how is equal to any says that each row, if any of these columns has a missing value, so it's just going to drop those rows. And the shape becomes 684. So it goes from 801 to 684. So that's a lot of missing values, right? And that's pretty typical. That happens all the time. Another thing we want to see is this particular label called is legendary. And what value counts function does is the same as something that you'll have on your notebook. Basically, seeing what different values do we have and how many of them do we have. I think in your notebooks, you'll have the rows printed by sum of each of these values. So you'll see 677 rows which have 0 as their legendary, which are not legendary, and 7 which are legendary, right? And okay, so for the missing values, how do we address them? Usually you can drop them, but instead of losing important data, what we can do is we can use this imputer object. Imputation means missing values are replaced by something that is similar. So in this case, what we're going to do is we're going to fill the missing values by the mean of that column. And simple imputer given by SKLearn.impute is a very helpful way to do it. And if you run this, what we're doing here is we create a simple imputer object, which will go and compute all the means for non-missing values for the column. And then it's gonna, so we're selecting only the numerical data. And once it's fit on that numerical data, that is, it computes all the means, we're gonna transform, which replaces the missing values by the means of that columns, but not in place. So the imp will not contain the missing values itself. We're just printing what if we do transform. And if we run that, we get for the column, for the fifth numerical column, percentage male, you'll see 1, 2, 3. Well, I guess it's hidden right now. But basically, if you were to expand it, you'll see that missing values have been replaced by the means of that column. And then now what we want to do is replace all the data that's in here, all the numerical data that's in here with the imputed data, that is missing values replaced by the means. So that's what we're going to do. So first of all, we'll make a data frame just to visualize all the data that we have. And here you can see 55.155 is the mean for the percentage male, and that's what the missing values are replaced by. Right. And then again, this is the second, and I think the last change that I've made in the notebook, unfortunately. But basically, the line in your notebook is doing the same thing. It's just replacing the data, the numerical data, by the new data that we have after imputation. So it's replacing each column, assigning each column, right? Right, and now let's move to the first machine learning algorithm that we're going to see. As Yash very well explained, naive Bayes that's what we're going to use for classification. And we're going to be predicting the Pokemon type for using a naive Bayes model. And in order for the machine learning algorithm to actually like keep track of the different Pokemon types, instead of using strings, we're going to assign a number to each of those strings, to each of those labels. And that's what the encoder object here is going to become. So using SKLearn preprocessing.label encoder, it'll assign each of those labels by a number. So for example, all these three would be having the same label, and then all these three would be having the same label. You can, and then you can assign a type enc column, which basically keeps track of the encoded number for that label instead of the label. And then we're going to just drop the type because we don't really need it. We are fine with the encoded version of that label. Just for interpretation, these are what the encodings are like. So bug is 0, dark is going to become a 1. And as you can see, it's going to arrange them in an alphabetic order and then assign all the labels an encoded value. And you can even check that. Right. So for our naive Bayes model, we're going to use only numerical data. We're going to remove all the categorical data. So we're going to select all these columns which contain numerical data information. And that's going to be our X. That is the input. And the output, the desired output, is going to be the type of the type encoded. So like it's going to be this column basically, right? So it has 20 labels that it has to predict the correct one from, and it has the numerical data. All right. Now we have all this X and all this Y, but before moving further, we have to get the training data and test data separate. Training data is what we're going to be training the model on, and then test is going to give us the performance. And that becomes what makes that convenient is the train test split function from SKLearn. And the train size we're going to be picking here, and usually in general practice, is 70%. So train size would be 70% of the total rows that we have, which is 801, I believe. And 801, 70% is like 560, and we can check that. So this is printing the number of rows in xtrain, and that's 560. And we're also looking at the head just to get a feel of that training data. So it's picking all these different rows randomly, because earlier we had the index arranged, right? Now it's random. Same for the test. All the other rows become our test data set. Right. Now this is going to be like a general kind of a pattern that we're going to see for all these machine learning models from SKLearn. We're first going to import an object, right? That's going to be the model that we're going to do stuff on. First thing we do with that model is going to be fitting the model using the train data. So we use the fit function, which takes the X train and Y train. And then we're going to predict from that model, from that fitted model, and then save the predictions as Y predictions, right? So we're just going to run this, and it's pretty fast, as you can see, since naive Bayes model is not a very complex model. Let's check the accuracy. And that accuracy score is 8.71%, which means that out of all the actual type encoded and the predicted type encoded, only 8% of the examples have correct predictions. So for 92% almost, it's predicting a wrong label. And that's pretty bad if you think about it. if you think about it, if I had to randomly just assign anything, the probability of getting a right label would be just 1 by 20, which is around what, 5%. And it's so close to that, right? The accuracy is almost randomly doing it, um, just twice as good as random, probably. So what are some reasons for that, right? What could be some reasons for that? And if you can even see here, this is printing the actual label and then the predicted label. And you can see that there's very less correlation between them, right? Okay. So the couple of reasons are, first of all, there's a lot of labels to predict, so it's very hard. Secondly, as Yash mentioned, naive Bayes has that naive assumption of like thinking that the features are independent when they're not. Right. And with that, let's move to the next algorithm. So K nearest neighbors. So KNN is a classification model that basically what we do is we pick the K nearest neighbors literally. So in the figure, you can see if our K is 3 and the star is what we want to predict the label for, if we look at the nearest 3 neighbors, then there's 1 yellow and 2 purple. And the majority being purple, we predict the star to be a purple. But if we used k equals 6, then we have only 2 purple and 4 of them are yellow. In that case, the star would become a yellow. And that's how the k nearest neighbors algorithm works. But now how do we choose k? So usually you can just choose k by trial and error. But what we're going to use in the notebook as well is we pick the k that gives us the best performance, as simple as that, the best one, right? But as the number of features in Canon increases, our model does start to become overfit, right? And that goes in general for most machine learning algorithms. And in our demo, sorry about that. In our demo, we're going to be trying to predict the is legendary feature first. So is legendary, as we saw, we have just 7 cases of no legendary, of not legendary, and 677, I think, of legendary examples. So it's not very balanced, but we hope that it still works. So we are selecting the features again, and these are, I think, these are all the numerical features again. And we again split the data set, and we are going to be using K 1, 2, 3, 5, 7, and checking the performance in all of these Ks. And then same thing, we create a model, but this time it takes a parameter, which is K, of course. And then we fit the model on training data set, and then we predict on the test data set and store the predictions. And the accuracy that we get are this. So for k equals 1, 92% of the times we are predicting correctly whether the given example is legendary or not, right? For 2, it slightly improves, then it decreases, and then it decreases for k equals 3, and so on. The best model that we see here is k equals 7, right? Because it gives us a 95% accuracy. And that's pretty good, actually. So we can run this model again for just that particular k, whichever we want. So we could choose 5, we could choose k. Let's just try with 5 first. And this is what the predicted and real labels look like. So in the fourth example, it's not legendary, and it does predict correctly. In the 721st example, it is legendary, but it's predicting as not legendary. And in fact, that's, I guess, a downside of having like an imbalance of class, because the model has seen more examples of not legendary. It tends to pick not legendary more often. But yeah, if you go into more advanced kind of metrics for machine learning, you'll see other metrics other than accuracy that you can use to evaluate your model. Right. So we're going to use KNN again, but this time we're going to be using it to predict the Pokemon type, which is the encoded value, that the type that we encoded, right? So same thing as we did with naive Bayes, but using KNN algorithm. And let's see, does KNN really improve our performance now? So this is what the data set is like, and we select the numerical data, and then we partition it, and we, again, pick different values of K. And this time, the only change we're doing is that instead of choosing is legendary as our Y, we're choosing type encoded as Y, and then just running the same thing. And okay, so accuracy reaches a maximum of 22% with K equals 7. Now, this is still not good, but it's still better than naive Bayes, which which um, which basically bolsters our both arguments. Naive Bayes, making that naive assumption, does not perform as good, and KNN does better because of that. But also, since this has so many labels, even KNN finds it hard to accurately model the type encoded. So for example, if we were to use K equals 10, in this case, since 7 gives us the best performance, we can even use 7. So we can just set the number of neighbors as 7, and that's the only change we need to make. And you'll see that, yeah, we see some correlations here, but for most of them still, it's not picking the right option, right? So another classification model that maybe could that we can also explore that's pretty frequently used, and one of the most standard classification models is logistic regression. But before I go into that, I would actually like to show linear regression, which is kind of a simpler version. So we talked about regression in general. And yeah, so linear regression is definitely a regression algorithm. And the thing in regression is they're built for continuous data. So for the first example that you see here, your X is continuous. So you see 11, maybe around 15, around 20, and goes on. But your Y is actually continuous too. You see 5, you see this dot having around like 6 point something, and then 7 points. So it's continuous. Whereas in this case, you see it's discrete. So you only see 0 as your Y, and then you see 1 as your Y. So linear regression is built for continuous data. And when we say linear, we mean that the slope is going to be constant. So the blue points here on the figure are actual points. And we are predicting, we basically regressed all these points and got a function that gave us this orange output. So our prediction for each of given X value would be this orange curve, this orange line. And what we'll be doing in the model as well is we're going to be using ordinary least square regression, which basically takes the difference between the orange line and the blue dot, that is the predicted output, and the real value, and then takes the square of those differences and then finds the average and then tries to minimize that cost, right? But when you use SKLearn, it almost becomes like a black box function. For classification, though, for discrete models, when y is equal to 0 and y equals 1 are the only options you see, linear regression seems kind of unfair or unnecessary. Why are we predicting so many points as non-zero and non-1, right? So that's when logistic regression comes into the picture. If you look at just the image, it's the same data points, but now instead of having a straight line, we have an S-shaped curve. So when X is around here, we predict very close to 0. And then we do start increasing, but very quickly, we start predicting values close to 1. And that's better for classification, especially for binary classification, when our options are true or false, as are Y. And this is still a regression because we are finding the equation of that sigmoid curve, the S-shaped curve here. And what we do is for the predicted value, we make a cutoff of 50%. So if the predicted value is less than 50%, we predict a y equals 0 label. And if the predicted value is over 50%, then we predict a label of y equals 1. And for this type of regression, since this is not linear, we cannot use ordinary least squares. Instead of that, we use the maximum likelihood estimation, which is commonly used for non-linear regressions like logistic regression. And that's what we're going to use in our example for predicting if a given Pokemon is legendary. So let's see. This is our data set. We take all the numerical features, and then we partition the data set using the 70% split. Again, it's very similar to the previous models. We have a logistic regression, and we have a parameter. We're using a parameter called maximum iterations. So maximum iterations means as we are finding the right sigmoid curve, the model starts with something completely random, a completely random curve, and then tries to improve iteratively. And by 500 iterations, we hope that it'll start predicting the right things. So that's what the maximum iteration parameter basically means. And then we try to fit it with training data and then get the predictions. And instead of looking at just the accuracy, this time, besides the accuracy, we're going to look at something called a confusion matrix, which can also be easily received by like the SKLearn metrics confusion matrix function. And all it needs is the test values, like the actual real test values, predictions, and the y values of the actual test data and the predictions for that test data. And what this confusion matrix basically means is that we have 216 true positives. That is, the data was legendary and was predicted as legendary. And then we have only 10 cases in which the data was actually non-legendary and was predicted as non-legendary as well. So you can notice that in this model, the rows are basically if the model is, the rows are basically what the model is predicting, and the columns are what it actually is. Or it might be the opposite, actually. You can check the confusion matrix documentation for confirming that, but what we can see is that one side is heavily biased. So 228 times, yeah, I think the rows should be, can you confirm, Yash?
Yeah, so the top to bottom gives true positive, true negative. So yeah, so that, okay, so true
positive, then
yeah, so positive would be the left side,
right,
and
positive,
negative is the right side.
right.
And then yeah, so the top left is true positive, the bottom right is true negative.
Yeah.
And then the bottom left is false positive, the top right is false negative.
It's false positive and false negative.
Yeah.
So
but also there are different orientations for it.
Yeah.
You could go to the documentation, and there are different ways to lay it out, but the default is how it's written in the comment. But yeah, it's always good to check the documentation, check it out.
Right. So this is true positive, this is false positive. So actual data has 228 total examples of positives, 216 plus 212, sorry, 216 plus 12. And out of those, 12 are predicted wrongly. 12 are predicted as not legendary. All right. And the accuracy is 94%, which is a bit lower than the best model of Canon, but the advantage in logistic regression is that we don't have to choose a K. We can just get one model and gives a great accuracy. Right. Our second last task for today is going to be multiple linear regression. Before that, since we are reaching the official end of the workshop, I'm so sorry about that, going over time. I would just take maybe 1 or 2 minutes. Like, if you have any questions, please let me know. I think that's for sure more important for the in-person component. I mean, synchronous component on it, not in person. If you have any questions, please let me know. All right.
Yeah, I think if you just want to
So,
give a quick overview of them, and then just run through the demo real quick in the next like 5 minutes. Yeah.
right, that works. I can do that. So the last model that we're going to be discussing is k-means clustering. I think we have a demo on multiple linear regression actually first. Never mind. Right. So, right. So we'll come to clustering in just a bit. So linear regression, we're trying to like predict the I don't know what HP stands for, health points, right? So that's what we're going to try to predict in this section, and we're going to be using the other numerical data for this. So we take all the features that we need, and we're going to set the health points as y. We're going to partition it at 70%, and then build a linear regression model and then fit using train. Instead of accuracy, the metric that you're going to be using here is called mean squared error, or mean absolute error is another valid statistic. You could also look at root mean squared error. And the lower these values are, the better your model is. So you want these errors to be as less as possible. And although it's not as intuitive as accuracy, but you can, yeah, you can see that all these values are pretty close. So 35 is pretty low, and predicted is pretty low compared to 416, which is pretty high, and 73 is also pretty high. Right. So moving to clustering now. Clustering is unsupervised learning, and we don't have any training data set or test data set. It just looks at the whole data set combined, and then it tries to split that into categories that it builds off its own. We're not providing any categories that it looks at and tries to infer. It's only trying to make its own categories by itself by using the whatever the algorithm tells it to. So let's look at this example. In k-means clustering, we suppose in this case, we look at k equals 2. So we're going to have two means here indicated by the cross. And the green means that it's not split into any categories first. We find two random points that are as far as possible from each other. And we then find all the points that are closer to the red mean than the blue mean, and that's our first iteration of having k-means cluster. So in this iteration, all of these points, the left points are red, and the right points are blue. But you can see that this is definitely not. It can definitely do better, right? The model can definitely do better. So it says it tries to find the new mean of the points that are selected here on the left, and that becomes this new red cross over here. And for the blue cluster, it tries to find the new mean again, and that becomes this cross. Then it does the same thing again. So it assigns all the points that are closer to the red as a red cluster, and all the points that are close to the blue cross as a blue cluster. And when that happens, it reaches a condition, and that condition is that the new clusters are so if we suppose we find new means after this, right? The new cluster over here, the new mean over here is this red X, and the new blue mean is this this blue cross. Now, if we were to split clusters based on these new means, they don't seem to change, right? They're the same. Each point that was in the red here is in the red here as well, and each one that's in the blue here is in blue here as well. So that's when the model is going to stop. You can also stop at maximum iterations, but that is definitely a condition. Okay, the model cannot do better than this because it's not going to find any new means. It's not going to find any new clusters. And this is going to only work for numerical inputs because what we're using here as the cost, or what we're finding the mean of in this k-means clustering is distances, the coordinates of the points. And I'm going to go. I'm going to quickly run over the example that we have in the notebook. So we're going to be clustering based on attack, defense, only, just these two features. And let's see how it performs. So similar to what we did before, we make a model first with all the parameters. What parameters do we have? So we're going to be looking at three means. So our k is equal to 3. Then we're going to initialize those means, those crosses, as random points. Then we're going to so this and it is, I think, is going to be the random seed that it's going to be using to set the initial points, and then it's going to go up till 300 iterations, or when it reaches this point where it cannot find any other new clusters. So that's why it's the max number of iterations. Right. So let's start with that and fit the model. And as you can see, the fit and predict is the same function literally. And why is that? Because we don't have a different data set, right? We don't have training data set. We don't have test data set. So we just need to fit on the same model and then predict on the same model. So we're just going to save all those clusters by fitting and predicting on the data set, on the whole data set. And these are what the clusters look like. That should be pretty intuitive, right? Well, we can do better for sure. We can visualize these on a scatter plot, and we can plot the attack and defense and show all these clusters using different colors. And that's what this cell does. So on the x-axis, you have attack, and y-axis, you have defense. And in these points, not only can you see all the data points, it's also showing you what the final means look like, the centroids. The crosses that were here, the red and the blue crosses, it's showing you those points as stars here. And we can see that that's a pretty nice way to split the given data. They seem to be forming nice groups over here. If it was to try to be any further better, we wouldn't be able to go, because most of the points that are here, their centroid right now is, even if we found all the points that are closer to this centroid than any other centroid, we would get the same points. So it's at that condition where it can't improve further for the most part. And yeah, so that's what clustering looks like. And that's the main algorithms that we wanted you to understand for an introduction to machine learning, because these are the most generally practiced and basic models. And yeah, that is all. Thank you so much for coming, and sorry for going 1 minute over time. And any questions would be welcome now. Any questions, theoretical?
Yeah, thanks for showing up on a Thursday evening. If you have any questions, you could always email us. Yeah, we can put our emails in the chat. Yeah, thank you so much for coming by, and yeah, have a great rest of your evening.